Okay, we are now going to continue by support and locomotion in non-muscular organisms. What do we mean by non-muscular organisms? Are those organisms that do not have what you can consider as the muscles. Here we are having the examples of different organisms which are non-muscular. We are having an example of amoeba, we are having an example of paramecium, and an example of that's said to be the iguana. You see, those are the non-muscular organisms which that we are going to look for their locomotion. Non-muscular locomotion is identified in animals that belong into Protectista kingdom. The Protectista kingdom is this of non-muscular organisms, where we saw their locomotion is propelled by. Here we said their locomotion is propelled by the mass, depending on individual animal. Locomotion is either amoeboid, is ciliary, or flagellated, or iguanoid type. Here it depends on how an organism is made. You see, if it is amoeboid, it is from amoeba, where using their cydopodia. In ciliary, in paramecium, we are using the cilia, and flagellated in iguana or iguanoid. It is in iguana, we are using the flagella. Here they use the cilia. Here amoeba move by amoeboid locomotion. Here by putting out cydopodia. It has the cydopodia. The cydopodia are these parts. The cydopodia are put out, and then it moves by from place to another. Locomotion is not maintained in any particular direction for long. Amoeba is constantly changing shape as it changes direction. You see, by their foldings, it moves by cydopodia by foldings. When it folded, it changes direction and changes the shape time by time by moving. So amoeboid locomotion is brought about by cytoplasmic streaming and between a jelly and soil states. That's understandable, I think. This cytoplasmic streaming requires calcium ions and ATP energy. Yes, it requires the calcium ions and requires ATP. Amoeboid locomotion is common to all rhizopods, including amoeba and white blood cells of the vertebrates. Yes, the white blood cells in the vertebrates can move amoeboid by amoeboid movement or amoeboidically. And also amoeba can move by this process, by this type of locomotion. You see how the amoeba is, and something like the cydopodia are these ones. You see the other parts. This is the cell membrane, as you see, contractile vacuole, nucleus, food vacuole, this one, and this is the cytoplasm. But necessarily, as we are looking at their movement, we are looking importantly at the cydopodia, those which makes the foldings for changing direction and shape in it. You see, this is a paramecium, where I see ciliary movement by using the cilia. These hair-like surrounding the the surface of a paramecium. You see the other parts. We are looking also at the egrena. Egrena has a flagellum. A flagellum used for movement. The flagellated organisms also use the flagellum. And you see the parts of the egrena as it is. So we are only looking at the flagellum, looking at the cilia on this, looking at the cydopodia on this, because we are talking about their mode of locomotion. Now we are seeing paramecium moves by means of cilia, and egrena moves by using by use of flagella. Cilia and flagella have similar structures, except that the cilia are short and many. Yes, you see, when observing this, when observing the paramecium, you find the cilia and the flagellum are hair-like. But here on the paramecium, the cilia are very short and are very many on a whole surface of the paramecium. You see, both cilia and flagella consist of fine tubes. They consist of fine tubes composed of an extension of plasma membrane. Yes, they consist of fine tubes composed of extension of plasma membrane. Egrena have an intricate cell membrane called a pericle. Egrena have an intricate cell membrane called the pericle. The pericle is this one. We say intricate because it has a great deal of fine details, or it is complexity. It is a complexity. Yes. Here also you see the letter is folded. The letter is folded into ribbon-like ridges, and each ridge is supported by microtubules. The pericle is tough and flexible. The pericle is tough, this one, and flexible, letting egrena crawling through mud when there is not enough water for them to swim. Here you see, as it can use its flagella, which seems as a tail, and use it helping in crawling with their body. Can crawl with their body, which is tough and flexible when in the environment of mud, when in not enough water for swimming. During cilia or flagellum locomotion, tubules slide past each another in a movement similar to that of actin and myosin similar to that of actin and myosin filament in skeletal muscles. You see, during cilia or flagellum locomotion, tubules slide past each other. Yes, they move on one another, one moving like passing one another, but with a movement of sliding, in a movement similar to that of actin and myosin filament in skeletal muscles. Hence, calcium ions and ATP are also required in the ciliary locomotion. Yes, they need calcium ions and need an energy, need ATP as energy. Here, I think this is understandable. We may even continue with the locomotion, support and locomotion in fish. When you continue in fish, support and locomotion, here you see the examples of fish as you observe. Then fish, like other aquatic animals, are adapted to such habitat in terms of locomotion due to its structural adaptative features, particularly secreton, which gives shape as well as muscles arrangement and swim bladder. These ones are adapted like other organisms in their aquatic movement. We have seen how they move in water. So they have the features or the characteristics that helping them in moving in water. They swim. Adaptative features of the fish for locomotion in water. The adaptative features, the first one, they have streamlined body shape. The streamlined body shape of the fish reduces friction between water and fish. Yes, as it is formed in this form. This said to be their streamlined body shape. It is in this form which reduces the friction between it and the water, so facilitating the movement. The body of the fish is mostly covered by scales, which overlap one another and point backward and lie close to the body. You see, their body is covered by the scales. The scales are these ones, and pointing back, where lies each close to the body. The scales are covered by mucus, which reduces the drag. Yes, you see, the scales of these fish are covered with what? With the mucus, and the mucus reduces the drag. Here, everybody can understand when adapted. We are when looking at the adaptation of the fishes, we look at the streamlined body shape. We are looking at how the body is covered by the scales. We are looking at the form, how the overlapping of the scales, how they are pointing back and closing to the body, closing to the body, and we see how the body is covered by the scales are covered by the mucus, and the role of the mucus is to reduce the drag. Here we are observing also the figure which shows how the fish is. The fish is this one. We have the pectoral finis, dorsal finis, and pelvic finis. We have annual fin and the caudal finis. Here, the tail or caudal fin has a large surface area. Yes, the tail or caudal fin has a large surface area, which increases the amount of water that is displaced, as it provides much of the push during swimming. Here, everybody has to understand it has the tail and the caudal fin has a large surface area. This large surface area which increases the amount of water that is displaced as it provides much of the push during swimming. Yes, it swims by pushing. Pair of pectoral and pelvic fins brings about downward and upward movement. Yes, pectoral fins brings about downward and downward movement. Yeah. With pectoral fins, the control of direction of the fish in water is possible, whereas the pelvic fins brings about the balance, preventing diving and rolling. Yes, you see the role of the pelvic fins. It's to bring about the balance and preventing diving and rolling. There are also a paired dorsal and anal fin. Anal fin for stabilizing the fish and thus preventing it from rolling or yawing. You see, the fish, there it is told, the fish has an paired dorsal fins and anal fins or anal fins for stabilizing the fish and thus preventing it from rolling or yawing. Yes, rolling or yawing. You see those preventing for rolling or for rotation. Fish is also adapted to locomotion in water by its strong tail muscles and highly flexible vertebrates column, which enables the tail to move from side to side against water. Here you see the fish, we are finding that it has another particular adaptation considering to the other organisms, to the other animals. In its locomotion in the water, you see it uses the tail muscles, which move side to side because they are flexible and they are moving moving against water. Yes, these are moving against the water, side to side. In addition, inflexible head and neck maintain forward thrust. It has an inflexible head and neck which maintained forward thrust. Internally, a fish is adapted to swim by swim bladder and muscles. You see their head, this part is inflexible and their neck is inflexible for focusing on the forward movement. Here it is understandable, I think. Air or gas-filled sac called the swim bladder. The gas-filled sac called the swim bladder outgrowths of the pharynx helps a fish to change its its buoyancy as it alters the gas pressure in the bladder. Everybody knows what we consider as swim bladder. The swim bladder on the fish. Swim bladder on the fish. It is this one. This part in the fish. The swim bladder. Where we are finding it inside. It has the swim bladder and the muscles. This one, it is the air or gas filled sac. This it is where the gas or air is filled. And this is it is it outgrowth or of the pharynx. Pharynx from the sides of the air, from the pharynx helps the fish to change its buoyancy as it alters the gas pressure in the bladder. Here, the pressure of the gas get changed because of that air filled sac. The air sac in it. Here, this still looking at this air sac. Air filled sac helps helps a fish to change its buoyancy or as it alters the gas pressure in the bladder. This means what? It protects for this buoyancy. For this buoyancy, the property of that facilitating it to float is still floating on the water. Because if does not having the ways of changing the pressure, it can even immerse immerged in water, but it is not. It still remain in floating because of that air sac. Now, so that it floats at any depths in water without using its muscles. Yes, float on any depths without using its muscles. Swim bladder also helps fishes to maintain a density that is equal to that of the surrounding water. It has first the role of changing its buoyancy as alter. Then also it is to maintain the density as equal to that of the surrounding water. Muscles or myomeres, those are segments or sheets of the muscles separated from its neighboring by the sheets of the connective tissues, enable fishes to move in water, owing the shapes of the muscles that are located on their sides of vertebral columns. You see, when moving, it has the muscles which are somehow separate one to another, then those helping it to move as the water passing between. We have the myotomes contribute to the mechanism of swimming by its arrangements. Yeah, they may be parallel, V-shaped or W-shaped, arranged in bundles or blocks that are separated by a myoseptum. You see, it has the myometer that to contribute to the mechanism of swimming, swimming in its arrangement. Yeah, where they may be parallel, they may be V-shape, they may be W-shape, arrangement of the bundles or blocks, yes, in the form of blocks that are separated by myoseptum. Although there are such arrangements, the myoseptal organization and orientation of fibers is complex. Yes, the myoseptal organization and orientation of fibers is complex. In bony fish, myomeres are V-shaped with new myomeres added posteriorly. With those myotomes, a fish swim by passing a wave of contractile muscle from anterior to posterior. We are saying with those myotomes, a fish swim by passing a wave of contracting muscle from anterior to posterior. This is understandable, I think. When a fish is moving, makes the waves of water from anterior to posterior, from front side to posterior side, or to the hind side. The muscles near the head of the fish contract fast, and the contraction proceeds posteriorly down the head, the length of the fish to the caudal fins. I think this is understandable. The muscles near the head of the fish contract fast, and the contraction proceed posteriorly down the length of the fish to the caudal fins. I think you have seen the caudal fins, which means the caudal fins are these ones. So the muscles contract from here at the head, following the structure of the fish. Then the others are until caudal fins. You see? Thus, a fish move forward from the contraction and the relaxation, yes, antagonistically of the myotome, of the myotome, or on either side of the body. Yes, one is contracting while another is relaxing. That taking place differently and facilitating the movement of the fish to move forward. An undulatory swimming of the fish is also powered by the segmental body musculature. An undulatory swimming of the fish is also powered by the segmental body musculature of the myotomes. Myotome and myosepta orient more perpendicularly to midline, yeah, to push aside, yeah. Here we are saying the myotome and the myosepta orient more perpendicularly to midline to push side, to push aside. Therefore, the fish can bend laterally with contraction muscle fibers shorten by half their length while maintaining volume without myoceptor, but simply a series of interconnected muscle fibers. Then the wave would be much dampened, much without myoceptor, but simply a series of interconnected muscle fibers. Then B wave would be much dampened. Yes, this I think it is understandable. We are looking at how a fish can get adapted in its locomotion, in its movement. We are discussing about the parts of the fish that's helping it in movement. We are stopping by the ambulatory swimming of the fish, where is also powered by the segmental body musculature of the myotomes. This, it has the segment of the myotomes, where the myotomes and the myoceptor orient more perpendicularly to the midline to push aside. And therefore, we are seeing that the fish can bend laterally with the contraction muscle fibers shortened by the half their lengths. Shortened by half their lengths, while maintaining volume without myoceptor, but simply a series of interconnected muscle fibers. Then the wave would be much dampened. This is understandable. I think one is going to generate the question, and I'm going to generate the answers for you. Thank you.